The universe consists of millions of unique stars and galaxies, each spinning in the massiveness of space. Scientists, through meticulous observation and advanced technology, have discovered that the universe is not static. It is expanding and in all directions. This discovery brings us to a mysterious question. What is it expanding out from? What lies at the center of the universe? The universe, as observed by astronomers, stretches over 93 billion light-years in diameter, a number that translates to an almost incomprehensible scale for the human mind. This measurement, however, only encompasses the observable part of the universe, the region from which light has had time to reach us since the Big Bang occurred around 13.8 billion years ago. Beyond this observable limit lies the realm of the unknown, potentially extending infinitely into space. At the foundation of modern cosmology is the Big Bang theory, which proposes that the universe began as an infinitely dense point, or singularity, which has been expanding ever since. This theory is supported by two pivotal pieces of evidence: the redshift of distant galaxies, indicating that they are moving away from us, and the cosmic microwave background radiation, a faint glow left over from the early universe. These observations suggest that the universe is not static but dynamic, continuously expanding and evolving. As we peer deeper into the universe, we encounter phenomena that defy conventional understanding, such as black holes, regions of space where gravity is so strong that not even light can escape. These cosmic enigmas are not just points of interest for scientists, they are fundamental to our understanding of the universe's very fabric. Diving into the depths of cosmic vastness, we grapple with the sheer scale of the universe, a concept that stretches the bounds of human imagination. Scientists estimate the observable universe, the portion from which light has reached us since the beginning of time, spans about 93 billion light-years in diameter. This staggering figure is merely a glimpse into the full expanse, which may extend far beyond what our current instruments can detect. To put this into perspective, a light-year, the distance light travels in a year, is about 9.461 trillion kilometers. This means the full stretch of the universe we can observe encompasses an almost unimaginable breadth of space. The enormity of the universe is not just in its physical size, but also in its content. It houses over 2 trillion galaxies, each with hundreds of billions of stars, and many more planets, asteroids, and comets. This vast collection of celestial bodies, each with its own unique properties and potential for life, underscores the diversity and complexity of the cosmos. In the grand scheme, Earth occupies a minuscule portion of the universe. The Milky Way, our galaxy, which seems boundless from our vantage point, is but a single speck in the cosmic ocean. Our Sun, although it may seem unique and central to us, is one of over 200 billion stars in the Milky Way. And our galaxy, in turn, is just one of the countless collections of stars and planets weaving through the vast expanse of space. This immense scale brings with it a sense of wonder and humility, reminding us of our place in the universe. It challenges us to push the boundaries of our knowledge and technology to explore beyond our local neighborhood. The endeavor to map and understand this expanse drives scientific inquiry, leading to innovations in technology and a deeper understanding of the laws that govern the cosmos. As we extend our gaze deeper into the universe, we also journey back in time. The light we see from distant stars and galaxies has traveled for billions of years to reach us, offering a glimpse into the past of the universe. This unique aspect of cosmic observation allows scientists to piece together the history of the cosmos, from the fiery aftermath of the Big Bang to the formation of galaxies and the birth of stars and planets. The scale of the universe, with its billions of galaxies and trillions of stars, highlights not only the vastness of space, but also the potential for diversity and complexity within it. As we further explore the cosmos, we delve into the composition of the universe, a subject that has fascinated scientists and laypeople alike. At its core, the universe is a blend of vast emptiness punctuated by celestial objects and mysterious forces. Understanding these components helps us grasp the intricate tapestry of existence that stretches across the vast expanse of space. The universe's backbone is made up of galaxies, massive structures that house stars, planets, nebulae, and various forms of matter and energy. Within these galaxies, stars form the most visible component, nuclear furnaces that fuse hydrogen into helium, producing light and heat. Our Sun is one such star, providing the energy necessary for life on Earth. Surrounding the stars are planets, moons, asteroids, and comets, each playing their role in the cosmic ballet. Yet what we see is only a fraction of the universe's true composition. Dark matter, an unseen and yet undetected form of matter, constitutes about 27% of the universe. It doesn't emit, absorb, or reflect light, making it invisible and detectable only through its gravitational effects on visible matter. Dark matter's presence is inferred from the way galaxies spin and how galaxy clusters stay together when the visible matter isn't enough to account for their observed gravitational effects. Even more elusive than dark matter is dark energy, which makes up about 68% of the universe. Dark energy is a mysterious force that's driving the accelerated expansion of the universe, a discovery that has revolutionized our understanding of the cosmos. Unlike dark matter, which pulls objects together, dark energy seems to push them apart, working against gravity on the cosmic scale. The remaining 5% of the universe consists of ordinary or baryonic matter. This includes everything made of atoms, from planets and stars to humans and the air we breathe. Despite being a small fraction of the total, this matter forms the basis of all known life and the structures we observe in the night sky. Interstellar and intergalactic spaces are filled with a thin soup of gas and dust, the remnants of dead stars and the building blocks for new ones. These regions are where new stars are born, in nebulae, where gas and dust clouds collapse under their gravity, igniting nuclear fusion. Cosmic microwave background radiation, a relic from the universe's birth in the Big Bang, fills the universe, providing a snapshot of the infant cosmos. This radiation is a whisper from the past, offering clues about the universe's earliest moments and its subsequent expansion. Gravitational forces, the glue that holds the universe together, dictate the motion of celestial bodies, from the orbits of planets to the formation of galaxy clusters. Gravity is the architect of the universe's large-scale structure, shaping the web of galaxies and the voids between them. Now let's explore what the observable universe is. The term observable universe refers to the segment of the entire universe that we can, in principle, observe from Earth. This concept is crucial in cosmology because it bounds the vastness of space from which light or signals have had enough time to reach us since the universe's inception approximately 13.8 billion years ago. The observable universe is a sphere with the Earth at its center, extending out to the farthest reaches of space from which light has traveled to us. Given the speed of light is about 299,792 kilometers per second, the observable universe extends outwards to about 93 billion light-years in diameter, even though it might seem intuitive to think it would be 13.8 billion light-years across, considering the age of the universe. This discrepancy arises because the fabric of the universe itself has been expanding since the Big Bang, stretching the paths light travels through space. Within this observable domain, everything is visible and potentially knowable, from the ancient light emitted by the cosmic microwave background radiation, which is the afterglow of the Big Bang, to the myriad galaxies, each containing billions of stars and planets, all swirling in the vast cosmic dance. These galaxies are not just scattered randomly, but are structured in a cosmic web of filaments and voids, showcasing the universe's large-scale structure. The observable universe contains all the phenomena and objects that inform our understanding of cosmology. The life cycles of stars, the distribution of galaxies, and the very laws of physics as they manifest across the cosmos. However, it's essential to acknowledge that the observable universe is just a portion of the whole universe. Beyond its boundary lies the unobservable universe, which remains hidden from us because its light has not yet had time to reach Earth. The full size of the entire universe is unknown and may be infinitely large or loop back on itself in a way that defies simple explanation. By studying the observable universe, scientists can gather crucial insights into the universe's overall structure, age, and the fundamental processes that govern its evolution. This investigation is conducted through telescopes that capture light across various wavelengths, from radio waves to gamma rays, allowing us to see back in time to the universe's earliest epochs. Measuring distances in the immense expanse of the universe is a complex task that requires innovative techniques and a deep understanding of cosmic phenomena. Astronomers have developed a series of methods akin to a cosmic distance ladder, with each rung using different tools and observations to measure how far away celestial objects are. This ladder enables us to span the vast distances from our nearest neighbors in the solar system to the most remote galaxies observable. For objects within our solar system, distances are measured directly through radar. By sending radio waves to planets or moons and timing how long it takes for the waves to bounce back, scientists can calculate distances with remarkable precision. This method, however, is limited by the speed of light and becomes less practical for objects beyond our solar system. Moving up the ladder, astronomers use the parallax method for stars relatively close to us, up to a few hundred light-years away. Parallax involves observing a star from two different points in Earth's orbit around the Sun and measuring the slight shift in the star's apparent position against the background of more distant stars. This shift, though incredibly small, allows scientists to calculate the star's distance using geometry. The farther away the star, the smaller the parallax shift. For more distant objects, such as galaxies, astronomers rely on standard candles, objects whose true brightness is known. The most famous standard candle is a type of exploding star called a Type Ia supernova. These supernovae have a consistent peak brightness, so by measuring how dim they appear from Earth, astronomers can calculate their distance. The principle here is simple. The dimmer the light, the farther away the object. Another rung on the cosmic distance ladder involves using redshift, a phenomenon where light from an object is shifted to longer, redder wavelengths as it moves away from us. This is due to the expansion of the universe. The greater the redshift, the faster the object is receding, which allows scientists to estimate its distance. This method is particularly useful for measuring the distance to very distant galaxies and understanding the universe's large-scale structure. Each of these methods overlaps in certain distance ranges, allowing astronomers to cross-check and refine their measurements. This layered approach has been instrumental in constructing a comprehensive map of the universe's vastness, revealing not just the scale of cosmic distances, but also the expansion rate of the universe itself, known as the Hubble constant. Why can't we see beyond the observable universe? The boundary of the observable universe is not just a limit of our current technology, it's a fundamental boundary defined by the speed of light and the age of the universe. Since the universe is about 13.8 billion years old, the furthest regions from which light has had enough time to reach us mark the edges of the observable universe. Essentially, we can't see beyond this boundary because the light from there hasn't had enough time to travel to us since the Big Bang. The speed of light in a vacuum is a constant, approximately 299,792 kilometers per second. This universal speed limit means that there is a maximum distance over which interactions can occur or information can be exchanged. In the context of the universe, this also sets a limit on how far we can see. The observable universe extends out to about 93 billion light-years across, not because the universe is only that big, but because that's the extent of the universe from which light has reached us. Another reason we can't see beyond the observable universe lies in its expansion. The universe is expanding at an accelerating rate, which means that distant galaxies are moving away from us faster than the speed of light due to the expansion of space itself. This doesn't violate the universal speed limit because it's not the galaxies themselves moving through space at such speeds, but the space between us and them stretching. As a result, light emitted by galaxies beyond the observable universe may never reach us, as the space it needs to cross is expanding too rapidly. Moreover, the universe's expansion affects the light traveling through it, stretching its wavelength and shifting it towards the red end of the spectrum, a phenomenon known as redshift. For galaxies far enough away, this redshift can be so extreme that their light is shifted beyond the visible range and even beyond the range of our current instruments, rendering them invisible to us. The concept of the observable universe also hints at the intriguing possibility that there's much more to the universe than what we can currently observe. Beyond this cosmic horizon could lie vast regions of space with galaxies, stars, and phenomena yet unseen. The size of the entire universe, compared to the observable part, is a subject of ongoing speculation and study among cosmologists. Some theories propose that it could be infinitely large or significantly larger than the part we can observe. Our understanding of the universe and its limits is based on the principles of physics as we know them today. As our instruments become more sophisticated and our theories evolve, we may find new ways to probe deeper into the cosmos. However, the fundamental constraints imposed by the speed of light and the finite age of the universe define a horizon beyond which the universe remains shrouded in mystery. Gravity played the starring role in the drama of galaxy formation. Even in the nearly uniform early universe, there were slight variations in density. Regions that were slightly denser than their surroundings began to gravitationally attract more matter, becoming even denser in a self-reinforcing cycle. Over time, these regions of higher density became the seeds from which galaxies would grow. As these primordial clouds of gas pulled in more matter, they began to collapse under their gravity. This collapse caused the gas to heat up and eventually to form stars. These early stars were massive, burning hot and fast, and their lives were relatively short-lived. The deaths of these stars, in spectacular explosions known as supernovae, scattered heavier elements such as carbon and oxygen into space. These elements would become the building blocks for later generations of stars and planets. Over billions of years, these collections of stars and gas continued to merge and grow, forming the diverse array of galaxies we see today. The process is influenced by the dark matter that envelops these galaxies, providing the gravitational scaffolding around which galaxies form. Dark matter, though invisible and detectable only through its gravitational effects, is thought to make up about 27% of the universe's mass energy content and plays a crucial role in galaxy formation and evolution. Galaxies come in various shapes and sizes, from spiral galaxies like our Milky Way, with their elegant arms wrapping around a central bulge, to elliptical galaxies, vast collections of stars in more rounded distributions, and irregular galaxies that lack a defined shape. The interactions and mergers between galaxies also play a significant role in their evolution, often leading to dramatic changes in their structure and star formation rates. The formation of galaxies is a complex process influenced by the interplay of gravity, gas dynamics, stellar evolution, and the mysterious dark matter. This cosmic ballet of matter coming together under the force of gravity, stars igniting and dying, and galaxies merging speaks to the dynamic nature of the universe. As we peer into the night sky, each galaxy we observe tells a story of cosmic evolution, from the earliest moments of the universe's history to the richly structured cosmos we see today. Dark matter plays a pivotal role in the formation and evolution of galaxies, acting as the cosmic glue that holds these vast structures together. Although dark matter is invisible and does not emit, absorb, or reflect light, its presence is inferred through its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. Understanding dark matter is crucial to our comprehension of the cosmos, as it constitutes about 27% of the universe's mass energy content, compared to just 5% for ordinary matter. The role of dark matter in galaxy formation begins in the early universe, shortly after the Big Bang. The universe was initially nearly uniform, filled with a hot, dense plasma of particles and radiation. However, tiny fluctuations in density provided the seeds for structures to form. Dark matter, unaffected by the forces other than gravity that act on ordinary matter, began to clump together in these denser regions. These clumps of dark matter created potential wells, regions of space where the gravitational pull is stronger due to the higher density of mass. As dark matter accumulated, it began to attract ordinary matter into these gravitational wells. Gas followed the distribution of dark matter, pooling together in the dense regions. These areas of higher density became the birthplaces of the first stars and galaxies. The gravitational framework established by dark matter allowed ordinary matter to coalesce and cool, forming the structures that would become the building blocks of galaxies. Furthermore, the distribution and mass of dark matter dictate the shape and dynamics of galaxies. Spiral galaxies like the Milky Way are thought to reside in halos of dark matter that extend far beyond the visible edge of the galaxy. The rotational curves of these galaxies, which show the velocity of stars and gas as you move away from the center, do not decrease as expected with distance. Instead, they remain flat or even rise slightly, indicating the presence of a substantial amount of unseen mass attributed to dark matter. On larger scales, dark matter influences the motion and interaction of galaxies within galaxy clusters. The gravitational effects of dark matter help to bind these galaxies together, preventing them from flying apart due to their high velocities. The distribution of dark matter within clusters can be mapped by observing the gravitational lensing effect, where light from distant objects is bent around the mass of the cluster, distorting the appearance of the background objects. Dark matter also plays a role in the large-scale structure of the universe, the cosmic web of galaxies and galaxy clusters. This structure, consisting of filaments of galaxies separated by voids, arose from the gravitational attraction of dark matter. Dark matter's presence shaped the universe's architecture, guiding the formation of structures on the grandest scales. Dark energy is a mysterious force that permeates all of space, exerting a repulsive effect that accelerates the expansion of the universe. Unlike dark matter, which clumps together and attracts matter due to its gravitational pull, dark energy appears to work against gravity, pushing galaxies apart at an ever-increasing rate. Dark energy is thought to constitute about 68% of the total energy content of the universe, making it the dominant component in the cosmic energy budget. The concept of dark energy came into prominence in the late 1990s, when observations of distant supernova revealed that the universe's expansion is accelerating. This was a surprising discovery, as it had been assumed that the universe's expansion, driven by the initial Big Bang, would be slowing down due to the gravitational attraction of all the matter in the universe. Instead, these observations suggested that some form of energy was working to speed up the expansion. The precise nature of dark energy remains one of the most profound mysteries in physics and cosmology. It does not appear to cluster in the way that dark matter does, and its properties seem uniform across space. One of the leading theories is that dark energy is a property of space itself, as suggested by Albert Einstein's cosmological constant, a term he introduced into his general theory of relativity to allow for a static universe, and later called his biggest blunder after the discovery of the expanding universe. In this view, empty space has an inherent energy that exerts a push on the fabric of the universe. The effects of dark energy are most apparent on the largest scales of the universe. It influences the rate at which galaxies are moving away from each other, an observation that can be measured through the redshift of light from distant galaxies. As dark energy causes the universe to expand more rapidly, it stretches the wavelength of light traveling through space, making it appear redder than it would otherwise. Dark energy also has profound implications for the fate of the universe. If its density remains constant or increases over time, it could lead to a scenario known as the Big Rip, where the accelerated expansion of the universe eventually tears galaxies, stars, planets, and even atomic particles apart. Black holes are regions of space where the gravitational pull is so strong that nothing, not even light, can escape once it crosses the so-called event horizon. This boundary marks the point of no return and cloaks the black hole's interior from the outside universe. The concept of a black hole emerges from Einstein's theory of general relativity, which revolutionized our understanding of gravity. According to this theory, massive objects warp the fabric of space-time around them. The more massive the object, the greater the distortion. In the case of a black hole, this warping is so intense that it creates a well of gravity from which escape is impossible. Black holes can form in several ways, but the most common method is the collapse of a massive star. When a star at least 5 times the mass of our Sun exhausts its nuclear fuel, it can no longer support its own weight against gravity and collapses. For the most massive stars, this collapse results in a supernova, a stellar explosion that can outshine entire galaxies. What remains can be so dense that it forms a black hole. There are different types of black holes. Stellar mass black holes, which are formed from the collapse of massive stars. Supermassive black holes, which are millions to billions of times the mass of the Sun and reside at the centers of most galaxies, including our own Milky Way. And intermediate mass black holes, which bridge the gap between the first two types, though their formation process is less understood. The study of black holes is not merely an academic endeavor. It has practical implications for our understanding of the universe. For instance, the detection of gravitational waves, ripples in the fabric of space-time caused by the collision of black holes, has opened a new window into observing the cosmos, providing insights into phenomena that were previously invisible to us. Despite their reputation as cosmic vacuum cleaners, black holes do not actively suck in material from their surroundings. Instead, objects fall into them in the same way that planets orbit the Sun, through the curvature of space-time. When matter does fall into a black hole, it heats up and can emit X-rays, which we can detect with space telescopes. This process is one of the ways astronomers can identify black holes. Another fascinating aspect of black holes is the concept of spaghettification, which occurs when an object approaches a black hole. The differential gravitational pull stretches the object into long, thin shapes like spaghetti. This, among other phenomena, highlights the extreme environment around black holes and the ways they warp the fabric of reality. Black holes also pose intriguing questions about the nature of information and the ultimate fate of the universe. According to quantum mechanics, information cannot be destroyed, yet it seems to vanish in a black hole, leading to the black hole information paradox. Theoretical physicists, including Stephen Hawking, have proposed various solutions to this puzzle, pushing the boundaries of our understanding of physics. Neutron stars and pulsars represent some of the most extreme and fascinating objects in the universe, offering unique insights into the laws of physics under conditions that are unattainable in any laboratory on Earth. Neutron stars are the remnants left behind after a massive star explodes in a supernova, collapsing to a point where protons and electrons merge into neutrons. These stellar remnants pack a sun's worth of mass into a sphere only about 20 kilometers across, making them incredibly dense and creating an environment where the laws of quantum mechanics and general relativity intertwine. Pulsars, a subset of neutron stars, emit beams of electromagnetic radiation from their magnetic poles. As pulsars rotate, these beams sweep through space like the beam of a lighthouse. When the Earth lies in the path of these beams, we detect a pulse of radiation at regular intervals, hence the name pulsar. The regularity of these pulses allows for precise measurements that contribute to our understanding of the cosmos in several ways. One of the most profound contributions of pulsars to science was the indirect confirmation of the existence of gravitational waves. In the 1970s, astronomers Russell Hulse and Joseph Taylor discovered a binary pulsar system, 2 neutron stars orbiting each other, one of which was a pulsar. They observed that the orbit of the pulsar was gradually shrinking, consistent with the loss of energy through gravitational waves as predicted by Einstein's theory of general relativity. This discovery earned them the Nobel Prize in Physics in 1993 and provided strong evidence for the existence of gravitational waves, which were directly detected for the first time in 2015. Neutron stars and pulsars also serve as natural laboratories for studying matter under extreme conditions. The density inside a neutron star is so high that atoms are crushed, and the matter exists in a state known as neutron degenerate matter. The conditions inside neutron stars may also allow for the formation of strange matter, a hypothetical state of matter that is more stable than nuclear matter. Studying these objects can help physicists understand the behavior of matter at nuclear densities and test the limits of nuclear physics theories. Furthermore, the extreme gravitational fields around neutron stars provide a testing ground for theories of gravity. Neutron stars in binary systems, especially those paired with another neutron star or a black hole, can be used to test the predictions of general relativity in strong gravitational fields, including the effects of gravitational lensing and time dilation. Pulsars, with their precise and regular pulses, have been used as cosmic clocks to conduct experiments in relativistic physics and to improve our understanding of the interstellar medium. The timing of pulsar signals can be affected by the presence of gravitational fields, allowing astronomers to map the distribution of matter in the galaxy. The discovery of pulsars also has practical applications in the field of navigation. The concept of a pulsar-based navigation system, similar to GPS but for space travel, has been proposed. Such a system would use the known positions and timing of several pulsars to determine the location of a spacecraft in space, providing an autonomous navigation system for interplanetary or interstellar travel. Quasars, or quasi-stellar objects, are among the most luminous and powerful objects in the universe. They are the intensely bright centers of distant galaxies, powered by supermassive black holes. As matter spirals into these black holes, it heats up and emits a tremendous amount of light and other radiation, making quasars visible across vast cosmic distances. Despite their small size in comparison to their host galaxies, often no larger than our solar system in diameter, their brightness can outshine the combined light of all the stars in those galaxies. Quasars are not just spectacular to observe, they serve as beacons that illuminate the early universe, providing clues about the formation and growth of galaxies and black holes in the cosmos's first few billion years. The light from quasars travels billions of years to reach us, meaning we see them as they were when the universe was much younger. By studying quasars, astronomers can peer back in time, examining the conditions and processes that prevailed in the early universe. One of the key contributions of quasars to our understanding of the cosmos is their role in probing the era of reionization. This was a period in the universe's history, about 1 billion years after the Big Bang, when the first stars and galaxies were forming, and the intense radiation they emitted began to ionize the hydrogen gas that filled the universe, making it transparent to ultraviolet light. Quasars, with their powerful radiation, are thought to have played a significant role in this process. By studying the light from distant quasars, especially how it interacts with the intergalactic medium, astronomers can gather information about the state of the universe during and after reionization. Quasars also provide a unique tool for studying the distribution of matter in the early universe. As the light from a quasar travels towards Earth, it passes through intergalactic gas and dust, which absorbs some of the light at specific wavelengths. This leaves imprints in the quasar's light spectrum known as absorption lines, which can be used to map the distribution of matter between the quasar and Earth. This technique, called the Lyman alpha forest method, has revealed a complex network of gas clouds and filaments in the early universe, helping astronomers understand the large-scale structure of the cosmos. The relationship between quasars and their supermassive black holes offers insights into how these black holes grow and influence their host galaxies. The properties of quasars, such as their luminosity and the speed of the material swirling around their black holes, provide information about the mass of the black holes and the dynamics of their accretion disks. This, in turn, helps scientists test theories of galaxy evolution and the co-evolution of galaxies and their central black holes. The Big Bang Theory is the leading explanation about how the universe began. At its simplest, it says the universe as we know it started with an infinitely small, infinitely dense point called a singularity, which suddenly expanded about 13.8 billion years ago, leading to the universe that we know today. This expansion is not a blast from a specific location, but rather space itself expanding, meaning that every part of the universe is moving away from every other part. This theory is supported by multiple lines of evidence. One of the most compelling is the observation of the cosmic microwave background radiation, a faint glow left over from the early universe, first detected in 1965. This discovery provided a snapshot of the infant universe, showing it was hot, dense, and nearly uniform, with slight variations that would eventually become the galaxies and other structures we observe today. Another key piece of evidence comes from the observation of distant galaxies. Edwin Hubble, in 1929, discovered that galaxies are moving away from us in every direction, with those further away moving faster. This observation supports the idea that the universe is expanding, a prediction of the Big Bang theory. The theory also explains the abundance of the lightest elements, hydrogen and helium, observed throughout the universe, which were formed in the first few minutes after the Big Bang during a period known as nucleosynthesis. Over time, as the universe expanded and cooled, matter began to clump together under the force of gravity, forming stars, galaxies, and eventually the larger structure of the universe. The Big Bang theory provides a framework for understanding the cosmic background radiation, the distribution of galaxies, and the chemical composition of the universe, among other phenomena. Despite its name, the Big Bang was not an explosion in space, but rather an expansion of space itself. This distinction is crucial for understanding how the universe can expand from a point without having a center from which it expands. Rather, every point in the universe is moving away from every other point. The Big Bang theory has evolved over time, incorporating new observations and discoveries, including the accelerating expansion of the universe, which is attributed to dark energy. However, many questions remain, such as the nature of dark matter and dark energy, the cause of the Big Bang, and what, if anything, existed before it. The concept of the Big Bang as the origin of the universe has undergone significant evolution since its first formulation, reflecting a journey from a speculative hypothesis to the cornerstone of cosmological theory. This evolution has been driven by technological advances, theoretical breakthroughs, and a growing body of observational evidence. Initially, the idea of a universe emerging from a singular point was met with skepticism. The term Big Bang was actually coined by Fred Hoyle during a BBC radio broadcast in 1949, meant derisively to mock the idea of a universe emerging from a Big Bang. Hoyle himself advocated for a steady-state model of the universe, where new matter was continuously created as the universe expanded, maintaining a constant density. However, the steady-state theory would gradually be overshadowed by mounting evidence supporting the Big Bang model. One of the pivotal moments in the theory's evolution came with the discovery of the cosmic microwave background radiation by Arno Penzias and Robert Wilson in 1965. This faint cosmic afterglow, predicted by theorists such as George Gamow, Ralph Alpher, and Robert Herman, provided direct evidence of the universe's hot, dense origins, strongly supporting the Big Bang model over the steady-state theory. Furthermore, the detailed measurements of the CMB by satellites such as COBE, Cosmic Background Explorer, WMAP, Wilkinson Microwave Anisotropy Probe, and Planck have refined our understanding of the Big Bang. These observations have not only confirmed the Big Bang's predictions about the CMB's existence, but also provided insights into the universe's age, composition, and the distribution of matter. The theory has also incorporated the concept of inflation, a rapid expansion of the universe that is thought to have occurred in the first fractions of a second after the Big Bang. Proposed by Alan Guth and others in the early 1980s, inflation explains the observed uniformity of the CMB across vast distances and the seeds of large-scale structures in the universe. The discovery of the accelerating expansion of the universe in the late 1990s through observations of distant supernovae introduced the concept of dark energy into the Big Bang model. This mysterious force, which makes up about 68% of the universe, is pushing galaxies apart at an accelerating rate, a phenomenon that the original Big Bang theory did not anticipate. Today, the Big Bang theory encompasses not just the initial expansion, but also the formation of the first particles, atoms, stars, and galaxies, as well as the dynamic, evolving universe we observe today. It incorporates quantum mechanics, particle physics, and Einstein's theory of general relativity, making it a comprehensive framework for understanding the cosmos. Let's talk a bit more about the CMB. The cosmic microwave background is a faint glow of light that fills the universe, remaining from the early stages of the cosmos shortly after the Big Bang. This radiation is the oldest light we can observe and offers a snapshot of the universe just 380,000 years after its inception, a time when protons and electrons joined to form neutral hydrogen atoms, allowing light to travel freely for the first time. The CMB is essentially the afterglow of the Big Bang, stretched and cooled to microwave wavelengths by the expansion of the universe over billions of years. Its discovery in 1965 by Arno Penzias and Robert Wilson provided a major piece of evidence for the Big Bang theory, showcasing that the universe did indeed have a hot and dense beginning. What makes the CMB so crucial to cosmology is its uniformity and the slight variations it contains. Across the sky, the CMB is remarkably consistent, with temperature variations of just 1 part in 100,000. These tiny fluctuations are incredibly important because they represent the seeds of all the future structure in the universe, the galaxies, stars, and planets that exist today. The patterns of these fluctuations also give us insights into the composition and evolution of the universe, including the balance of matter and energy, the geometry of the universe, and how fast it is expanding. The temperature of the CMB is astonishingly uniform, about 2.7 Kelvin, minus 270.45 degrees Celsius, which is just above absolute zero, the temperature at which all motion stops. This uniformity confirms the universe's isotropy, meaning it looks the same in all directions, a principle that underpins modern cosmology. Over the decades, missions like the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and the Planck satellite have mapped the CMB with increasing precision. These observations have solidified the Big Bang theory and refined our understanding of the universe's early moments and its subsequent evolution. For instance, they have helped determine the universe's age with remarkable accuracy, about 13.8 billion years, and provided insights into the processes of cosmic inflation. Space-time is a concept that combines the 3 dimensions of space with the 4th dimension of time into a single 4-dimensional continuum. This framework is essential for understanding the workings of the universe under the theory of relativity, proposed by Albert Einstein in the early 20th century. According to this theory, the fabric of space-time is not static, but can be warped or curved by mass and energy. This curvature of space-time is what we perceive as gravity. Gravity's influence on space-time is a cornerstone of Albert Einstein's general theory of relativity, which provides our current understanding of gravitational phenomena. This theory revolutionized how we perceive gravity, moving away from the idea of a force acting at a distance, as Isaac Newton proposed, to a more profound mechanism. Einstein suggested that massive objects cause space-time to curve, and this curvature is what we perceive as gravity. Thus, gravity's effect on space-time is not just an interaction, but a fundamental alteration of the universe's fabric. Imagine space-time as a trampoline. When you place a heavy ball in the middle, the trampoline's surface curves downward. If you then roll a smaller ball across the trampoline, it will move towards the larger ball, not because the larger ball directly pulls it, but because its path is curved by the depression in the trampoline. This analogy helps illustrate how gravity works according to general relativity. Massive objects like stars and planets bend the space-time fabric around them, and other objects move along the curves in this fabric. The more massive an object, the more it warps the space-time around it. This is why the gravity of a planet like Earth affects objects on its surface and in orbit around it, while the far more massive Sun creates a much deeper curvature in space-time, keeping Earth and the other planets in orbit around it. The effects of this curvature are observable in phenomena such as the precession of Mercury's orbit, which couldn't be fully explained by Newton's laws alone, but was precisely accounted for by Einstein's theory. Gravity's effect on space-time also means that time itself is affected. Near a massive object, where space-time is significantly curved, time flows more slowly compared to a region of weaker gravitational fields. This phenomenon, known as gravitational time dilation, has been confirmed by experiments showing that clocks run slightly faster on satellites in orbit than they do on Earth's surface. The extreme effects of gravity on space-time are perhaps nowhere more striking than near a black hole. At the event horizon of a black hole, space-time is curved so much that the escape velocity exceeds the speed of light, meaning nothing, not even light, can escape once it crosses this boundary. This intense curvature near black holes also leads to dramatic examples of time dilation. Gravitational waves are another manifestation of how gravity affects space-time. When massive objects like black holes or neutron stars collide, they can send ripples through the fabric of space-time. Much like throwing a stone into a pond, creates ripples on the water's surface. These waves, which carry energy away from the cataclysmic events that produce them, were predicted by Einstein's theory and have been directly detected by the LIGO and Virgo observatories, opening a new window for observing and understanding the universe. Space-time is not just a backdrop against which events play out, but is dynamic and interacts with matter and energy. The presence of mass and energy changes the structure of space-time, and the curvature of space-time tells matter how to move. This interplay is described by Einstein's field equations, a set of 10 interrelated differential equations that form the core of the general theory of relativity. The concept also has profound implications for how we perceive time. In space-time, time behaves differently depending on the speed of an observer or the strength of gravitational fields they are in, a phenomenon known as time dilation. For example, clocks on satellites in orbit around Earth tick slightly faster than those on the planet's surface, a difference accounted for in the Global Positioning System, GPS, to maintain accuracy. Space-time also challenges our intuitions about simultaneity. Events that appear simultaneous to one observer may occur in a different sequence to another observer moving at a different velocity, illustrating the relativity of time. Wormholes, a theoretical passage through space-time, have captivated scientists and the public alike with the possibility of creating shortcuts between distant points in the universe. Stemming from the equations of Albert Einstein's general theory of relativity, wormholes suggest that the fabric of space-time can be bent and connected in such a way that dramatically reduces travel distances and times, fundamentally changing our understanding of space and distance. In theory, a wormhole would consist of two mouths connected by a throat, which could bridge vast cosmic distances or even different universes or times. The concept of a wormhole brings together many aspects of modern physics, including the ideas of space-time curvature and quantum mechanics, suggesting that these tunnels could exist at the quantum level as tiny, fluctuating passages. The most common type of wormhole considered by physicists is the Schwarzschild wormhole, also known as an Einstein-Rosen bridge, named after Albert Einstein and Nathan Rosen, who first proposed the concept in 1935. However, these wormholes would likely collapse too quickly for anything to travel through, according to current understandings. For a wormhole to be traversable, theoretical physics suggests the need for exotic matter with negative energy density to keep it open, a requirement that challenges our current understanding of physics and materials. If traversable wormholes exist or could be created, they would revolutionize our understanding of space and distance. The ability to travel through a wormhole would mean that distances that currently take light years to traverse could be covered in a fraction of the time, essentially enabling us to jump across the cosmos. This capability would not only revolutionize space travel, but also challenge our notions of causality and connectivity in the universe. Wormholes could offer unprecedented opportunities for scientific exploration and observation, allowing direct study of distant galaxies, stars, and planets within a human lifetime. They could also provide practical routes for interstellar travel and communication, breaking down the cosmic distances that currently make such endeavors prohibitively time-consuming. However, the existence of traversable wormholes remains speculative. While they are fascinating solutions to the equations of general relativity, there is no empirical evidence for their existence. Theoretical challenges, such as the requirement for exotic matter, raise significant questions about whether such phenomena could exist in our universe and be harnessed by future technologies. The implications of wormholes extend beyond the scientific to the philosophical, challenging our concepts of separation, isolation, and the very nature of the universe. If wormholes could allow for travel across time as well as space, they would open up even more profound questions about causality, free will, and the structure of time itself. The question of locating the center of the universe is intriguing and fundamentally challenges our understanding of cosmic structure. Contrary to what one might intuitively believe, modern cosmology, based on the theory of general relativity and the observations supporting the Big Bang theory, indicates that the universe does not have a center in the way we might think of a center in everyday contexts. The Big Bang theory, the prevailing cosmological model, describes the universe as expanding uniformly from a state of extremely high density and temperature. However, this expansion doesn't imply that the universe is expanding into something or from a specific central point. Instead, every part of the universe is getting farther away from every other part, much like how dots on a balloon move away from each other as the balloon inflates. This analogy helps illustrate the concept that, although the universe is expanding, it doesn't have a center point from which the expansion proceeds. Furthermore, observations of the cosmic microwave background radiation, the afterglow of the Big Bang, reveal a universe that is isotropic, meaning it looks the same in all directions to a high degree of precision. This uniformity supports the idea that no special point in the universe, including a center, can be distinguished based on the large-scale structure of the universe itself. The concept of the universe not having a center can be counterintuitive because our everyday experiences with physical objects suggest they all have centers. However, the universe's structure and expansion are governed by the rules of general relativity, which differ significantly from our everyday experiences governed by Newtonian physics. According to general relativity, space-time itself is what's expanding, and it does so uniformly across all of its infinite or sufficiently large and curved extent, making the concept of a center irrelevant. In theoretical models where the universe is finite but unbounded, much like the surface of a sphere, asking for the center of the universe would be akin to asking for the center of the surface of the Earth. There is no central point on the surface itself. Rather, every point can be considered equally central or equally peripheral, depending on one's perspective. The shape of the universe, and whether it is flat, open, or closed, is a fundamental question in cosmology, touching on the universe's overall geometry and its fate. This question revolves around the universe's density, which determines its curvature according to Einstein's theory of general relativity. The critical factor here is the density parameter, omega, which compares the actual density of the universe to the critical density needed for the universe to be flat. If the universe has exactly the critical density, meaning omega equals 1, then it is considered flat. In a flat universe, parallel lines never meet, and the geometry is Euclidean, just as it is in our everyday experience. The universe's expansion would slow down over time due to gravity, but it would never actually stop or reverse. Observations of the cosmic microwave background, CMB, particularly by the WMAP and Planck satellites, have shown that the universe is very close to flat, with omega very close to 1. This suggests that the universe is either perfectly flat or so close to flat that the difference is indistinguishable. If the density of the universe is less than the critical density, omega less than 1, the universe is open. In this scenario, the universe would expand forever at an accelerating rate, and its geometry would be hyperbolic. This means that, on a cosmic scale, parallel lines would diverge. However, current observations, including studies of the CMB and the distribution of galaxies, suggest that the universe is not open. If the density of the universe exceeds the critical density, omega greater than 1, then the universe is closed. It has a positive curvature, somewhat like the surface of a sphere, where parallel lines eventually meet. In a closed universe, gravity would eventually stop the expansion of the universe, leading to a contraction or big crunch. Like the open model, current data does not support a closed universe. Observations suggest that the universe's density is very close to the critical density, making it flat or nearly flat. The consensus among cosmologists, based on the latest observations, is that the universe is flat, or very nearly flat. This flatness has profound implications for the universe's fate, suggesting it will likely continue to expand forever, albeit at an accelerating rate due to dark energy. The exact nature of dark energy and how it affects the universe's long-term evolution remains one of the biggest questions in cosmology. The shape of the universe and its implications for concepts like a center intertwine closely with our understanding of cosmology and the nature of space-time itself. If the universe is flat, or nearly flat, as current evidence strongly suggests, this has interesting implications regarding the idea of a center to the universe. In a flat universe, which extends infinitely in all directions, the notion of a center doesn't apply in the traditional sense. Since the Big Bang occurred everywhere in space simultaneously, every point in the universe can be considered as both the center and not the center at the same time. This concept is akin to asking for the center of an infinite plane. While you can choose any point as a reference, no point serves as the central point from which everything else emanates. Moreover, the universe's uniform and isotropic expansion, meaning it looks the same in every direction and expands uniformly from any vantage point, further complicates the idea of a center. This uniform expansion, observed through the movement of galaxies and the cosmic microwave background radiation, suggests that all parts of the universe are moving away from each other without a central point from which this movement originates. In theoretical models where the universe might have a positive curvature, closed, or negative curvature, open, the concept of a center becomes even more abstract. A closed universe, analogous to the surface of a sphere, doesn't have a center within its three-dimensional surface. Instead, the center of curvature would exist in a hypothetical fourth spatial dimension, not accessible or observable to us. Similarly, in an open universe, the concept of a center is also not applicable, as the space extends infinitely in all directions with a hyperbolic geometry. Therefore, the flat or nearly flat shape of the universe, supported by current observations, implies that the universe does not have a center in a conventional physical sense. This insight is a fundamental departure from earlier Earth-centric or Sun-centric models of the cosmos, reflecting the evolution of our understanding toward a more complex and nuanced view of the universe's structure. The distribution of galaxies across the cosmos is not random but forms a vast and intricate pattern known as the cosmic web. This web-like structure consists of dense clusters of galaxies interconnected by filaments of galaxies, all separated by vast empty voids. This arrangement comes from the gravitational pull of dark matter, an invisible substance that makes up about 27% of the universe. Although we cannot see dark matter, its presence is inferred from its gravitational effects on visible matter, including the galaxies that light up our night sky. Galaxies tend to cluster together due to gravity. These clusters can contain hundreds or thousands of galaxies bound together by their mutual gravitational attraction. The largest clusters can span millions of light years across. Between these clusters are filaments, thinner stretches of galaxies that form the cosmic web structure, bridging the gaps between clusters and superclusters. Superclusters are even larger formations, comprising many clusters and groups of galaxies that can span hundreds of millions of light years. Our own Milky Way galaxy is part of the local group, which in turn is part of the Virgo supercluster. The voids between these structures are vast regions of space with very few galaxies. They can span tens to hundreds of millions of light years across. Despite their emptiness, these voids are an essential part of the cosmic web structure, influencing the motion of galaxies and clusters on the largest scales. The distribution of galaxies in the universe was shaped by the early universe's tiny density fluctuations, magnified by the cosmic inflation shortly after the Big Bang. These fluctuations became the seeds for the cosmic web, growing under the influence of gravity over billions of years. Dark matter clumped together in these regions of higher density, pulling in normal matter to form stars and galaxies. Observations from telescopes and satellite missions, such as the Sloan Digital Sky Survey and the Hubble Space Telescope, have mapped out the cosmic web in great detail, revealing the filamentary structure that connects galaxies across the universe. These observations have confirmed predictions from cosmological models and simulations, helping astronomers understand the universe's large-scale structure and its evolution over time. Telescopes are remarkable instruments that significantly extend our view of the universe, allowing us to observe objects billions of light-years away and to look back in time to the universe's early stages. They do so by collecting and focusing light and other forms of electromagnetic radiation from celestial objects, which can then be analyzed to determine the object's properties, such as their composition, temperature, distance, and motion. The primary way telescopes extend our view is through their ability to gather faint light over large areas and long periods, magnifying distant objects to make them visible or detectable from Earth. Larger telescopes can collect more light, which is why there is a continual effort to build bigger telescopes or telescope arrays. Telescopes operate across the electromagnetic spectrum, from radio waves to gamma rays, with different types designed to capture different wavelengths. Optical telescopes. These telescopes collect visible light using lenses or mirrors. They range from small backyard telescopes to large ground-based observatories and space telescopes like the Hubble Space Telescope. Optical telescopes have provided some of the most stunning images of our universe, from the detailed bands of Jupiter to distant galaxies. Radio telescopes. These collect radio waves emitted by celestial objects. Radio telescopes can be ground-based, like the Very Large Array in New Mexico, or space-based. They have been instrumental in discovering cosmic phenomena invisible to optical telescopes, such as pulsars, and mapping the cosmic microwave background radiation. Infrared telescopes. Infrared light penetrates dust clouds more effectively than visible light, allowing astronomers to observe regions of space that are obscured to optical telescopes. The Spitzer Space Telescope and the James Webb Space Telescope are examples of observatories designed to capture infrared light, offering insights into star formation and the early universe. X-ray and gamma-ray telescopes. These telescopes detect the high-energy emissions from the most violent and hot processes in the universe, such as supernovae, black holes, and neutron stars. The Chandra X-ray Observatory and the Fermi Gamma-ray Space Telescope have expanded our understanding of these extreme environments. By analyzing the light and other radiation collected by telescopes, astronomers can determine not just the location of celestial objects, but also their chemical composition, temperature, mass, and velocity. This information has led to groundbreaking discoveries, such as the accelerating expansion of the universe, the existence of exoplanets, and the detailed structure of cosmic web. Telescopes have allowed us to confirm the theories of relativity, understand the life cycle of stars, and observe the conditions in the early universe shortly after the Big Bang. They have been instrumental in identifying the dark matter through its gravitational effects and searching for signs of dark energy. Launched into orbit around Earth on April 24, 1990, the Hubble Space Telescope has revolutionized our understanding of the universe over the decades. Its position above the Earth's atmosphere allows it to capture images and data with clarity that ground-based telescopes can't match, free from the blurring effects of the atmosphere. This unique vantage point has enabled Hubble to make numerous contributions to the field of astronomy, providing insights into the cosmos's age, the existence of dark matter, the accelerating expansion of the universe, and the characteristics of exoplanets, among other discoveries. Determining the age of the universe. Hubble played a crucial role in refining measurements of the Hubble constant, the rate at which the universe is expanding. By observing distant galaxies and determining their red shifts and distances, Hubble has helped narrow down the age of the universe to approximately 13.8 billion years. This measurement is a key piece of the puzzle in understanding the evolution of the cosmos from the Big Bang to the present day. While Hubble did not discover dark matter, its observations have provided substantial evidence for its existence. By mapping the distribution of galaxies and observing gravitational lensing, where the gravity of a massive object warps the space around it, bending the light from objects behind it, Hubble has visually depicted how dark matter influences the structure and motion of galaxies and clusters of galaxies. In the late 1990s, observations made with Hubble contributed to the groundbreaking discovery that the universe's expansion is accelerating, not slowing down as previously thought. This acceleration is attributed to dark energy, a mysterious force that pervades all of space. This discovery was so profound that it earned the Nobel Prize in Physics in 2011. Hubble has been instrumental in studying exoplanets, planets outside our solar system. It has provided detailed observations of the atmospheres of several exoplanets, detecting elements such as sodium, hydrogen, and even water vapor. These studies are vital for understanding the composition and conditions of planets beyond our solar system, contributing to the search for potentially habitable worlds. Through its deep field images, Hubble has peered back in time to observe the early stages of galaxy formation. These observations have helped astronomers understand how galaxies evolve over billions of years, from young, chaotic collections of stars to the more structured forms we see today. Hubble has captured stunning images of nebulae, the birthplaces of stars, as well as the intricate remnants of stars that have exploded in supernova. These observations help scientists learn more about the life cycle of stars, from their formation in nebulae to their eventual demise, enriching our understanding of the universe's dynamic nature. Hubble has observed Cepheid variables, a type of star used as a standard candle for measuring astronomical distances. These observations have helped calibrate the cosmic distance ladder, a series of methods by which astronomers determine the distances to celestial objects, further refining our model of the universe's scale. In the quest to unravel the mysteries of the cosmos, observatories across the globe collaborate in a multifaceted dance of technology, data sharing, and joint missions, amplifying their individual capabilities to explore the universe. This global network of observatories, spanning from radio, optical, and space-based telescopes, harnesses the collective power of diverse instruments to provide a comprehensive view of the universe across the electromagnetic spectrum. One key aspect of this collaboration is the sharing of time-sensitive data. For instance, when a telescope detects a transient cosmic event, such as a supernova or the collision of neutron stars, observatories worldwide are alerted so they can immediately turn their instruments toward the event. This coordinated response allows astronomers to study these phenomena in multiple wavelengths, from radio to gamma rays, capturing crucial details that unfold at different times and in different parts of the electromagnetic spectrum. Interferometry is another powerful technique made possible through collaboration, where telescopes separated by vast distances work together as if they were a single telescope. This method, which can involve both ground-based and space-based observatories, dramatically increases the resolution and sensitivity of astronomical observations. The Event Horizon Telescope project, which produced the first-ever image of a black hole's event horizon, is a prime example. It linked radio observatories across the planet, creating a virtual Earth-sized telescope capable of observing the black hole at the center of galaxy M87. Space missions, too, benefit from international cooperation. Satellites and space telescopes often require expertise, resources, and technology from multiple countries. The Hubble Space Telescope, the James Webb Space Telescope, and the Chandra X-ray Observatory are examples where collaboration and shared use have led to significant advancements in our understanding of the universe. These space-based observatories complement ground-based observations, providing clear views of the cosmos unobstructed by Earth's atmosphere. Data sharing and open access to archives are also vital components of global collaboration. Many observatories make their data available to the international scientific community, allowing astronomers worldwide to conduct research and make discoveries, even if they don't have direct access to a major telescope. This openness accelerates scientific progress, with researchers able to analyze and reanalyze data, uncovering new insights into the universe's workings. Educational and public outreach is another area where observatories collaborate, sharing images, discoveries, and knowledge with the public, and inspiring the next generation of scientists and astronomers. Through coordinated events, such as live broadcasts of solar eclipses or passing comets, observatories help bring the wonders of the universe to people around the globe. The Standard Model of Particle Physics is a comprehensive framework that describes the fundamental particles and forces that govern the universe, except for gravity. Developed over several decades in the second half of the 20th century, the Standard Model combines quantum mechanics and special relativity to explain how particles interact through three of the four fundamental forces: the electromagnetic force, the weak nuclear force, and the strong nuclear force. Gravity, governed by general relativity, does not yet fit into this framework, highlighting one of the major unsolved problems in physics. At the heart of the Standard Model are the basic building blocks of matter: quarks and leptons. Quarks come in 6 flavors: up, down, charm, strange, top, and bottom, and combine to form protons and neutrons, which in turn make up the nuclei of atoms. Leptons include electrons, which orbit the atomic nucleus, and neutrinos, elusive particles that rarely interact with matter, as well as their heavier cousins, the muon and tau particles. Each particle has a corresponding antiparticle with opposite electric charge or quantum numbers. The Standard Model also describes force-carrying particles known as gauge bosons, which mediate the fundamental forces. Photons convey the electromagnetic force, responsible for electricity and magnetism. W and Z bosons mediate the weak force, which plays a role in nuclear decay. And gluons carry the strong force, which binds quarks together in protons and neutrons. The recently discovered Higgs boson, predicted by the Standard Model and confirmed by experiments at the Large Hadron Collider in 2012, is responsible for giving mass to other particles through the Higgs mechanism. Despite its success in explaining a wide range of experimental results and its precise predictions, the Standard Model is not considered the ultimate theory of everything. It cannot incorporate gravity, described by general relativity, nor explain the dark matter and dark energy that appear to dominate the universe's mass-energy content. Moreover, it does not account for the neutrino masses observed in experiments, suggesting the existence of physics beyond the Standard Model. Physicists are actively searching for signs of new physics that could extend or replace the Standard Model, exploring phenomena that the model cannot explain. These efforts include searching for supersymmetry, extra dimensions, and particles that could make up dark matter. Discoveries in these areas could revolutionize our understanding of the universe at its most fundamental level, bridging the gap between the Standard Model and a more comprehensive theory of everything. String theory and M-theory represent bold and intriguing efforts to address some of the most profound questions in physics, challenging traditional views by proposing a fundamentally different framework for understanding the universe's fabric. Unlike the Standard Model of particle physics, which describes the subatomic particles and forces using point-like particles, string theory posits that the universe's fundamental building blocks are not zero-dimensional points, but rather one-dimensional strings. These strings can vibrate at different frequencies, and the mode of vibration determines the type of particle the string represents, be it a quark, electron, photon, or any other fundamental particle. String theory emerged in the late 20th century as a potential candidate for a theory of everything, a framework that could unify all fundamental forces, including gravity, within a single theoretical structure. This ambition directly challenges traditional views in physics, which, despite the success of the Standard Model and general relativity, have remained distinctly separate in their descriptions of the universe. The Standard Model does not encompass gravity in a quantum context, and general relativity does not apply to the quantum scale. String theory offers a way to bridge this divide, suggesting that at the most fundamental level, all forces and particles are manifestations of one entity: strings. One of the most revolutionary aspects of string theory is its requirement for extra dimensions. While we are familiar with 3 spatial dimensions and 1 time dimension, string theory posits the existence of additional spatial dimensions, up to 10 in some versions of the theory and 11 in M-theory, a more advanced version that unifies various string theory formulations. These extra dimensions are thought to be compactified or curled up at scales so small that they are currently undetectable, which challenges our traditional understanding of space and offers new insights into the universe's structure. M-theory further expands on the ideas of string theory by suggesting that strings are not the most fundamental objects. Instead, it proposes that objects of various dimensions, membranes or brains for short, are fundamental, with strings being just one-dimensional examples. M-theory aims to provide a more complete and consistent framework that includes not only the particles and forces of the standard model, but also gravitational interactions in a quantum context, potentially leading to a unified theory of quantum gravity. String theory and M-theory challenge traditional views by suggesting a universe far more complex and interconnected than previously imagined. Their implications extend beyond particle physics and cosmology, touching on mathematics, quantum mechanics, and astrophysics. They offer potential explanations for the nature of black holes, the evolution of the early universe, and the fundamental structure of space and time. However, these theories also face significant challenges, primarily due to the current lack of direct experimental evidence and the difficulty in testing predictions made by string theory and M theory. In the quest to find life beyond Earth, scientists employ a set of criteria that focus on the conditions believed to be necessary for life as we know it to exist. This multidisciplinary search spans astronomy, biology, geology, and atmospheric sciences, among others, reflecting a comprehensive approach to one of humanity's oldest questions. The criteria are centered around the presence of water, the conditions of the planet's environment, and the chemical signatures that could indicate life processes. Water is considered a fundamental ingredient for life, serving as a solvent in which biochemical reactions take place. The search for extraterrestrial life often focuses on the habitable zone around stars, where temperatures are just right for liquid water to exist on a planet's surface. This zone varies depending on the star's size and temperature. Planets or moons that have evidence of liquid water, either currently or in the past, are prime targets for further study. Beyond water, life requires an environment where it can thrive. This includes a stable climate, a protective atmosphere, and the absence of extreme radiation or toxic substances. Scientists examine the size, density, and composition of exoplanets to assess whether conditions might be right for life. For example, a planet's atmosphere can provide clues about its surface conditions, potential greenhouse gas concentrations, and whether it has protective magnetic fields. Life processes produce chemical byproducts. By analyzing the spectra of light coming from planets, scientists can detect the presence of gases in their atmospheres that might indicate biological activity, such as oxygen, methane, and carbon dioxide. The simultaneous presence of certain gases, especially when out of chemical equilibrium, could suggest biological sources, as it does on Earth. Organic molecules, which are carbon-based compounds critical for life, are another key target. The detection of these molecules, particularly in places where liquid water is present or was in the past, would be significant. Complex organic chemistry, including amino acids and nucleotides, is considered a precursor to life. Life on Earth relies on various energy sources, primarily sunlight through photosynthesis. However, life can also thrive on chemical energy, as seen in deep-sea hydrothermal vents. In searching for extraterrestrial life, scientists consider alternative energy sources that could support life, especially on planets or moons where sunlight is scarce. The search for life beyond Earth is not just about finding organisms directly, but identifying environments where life could exist or could have existed in the past. This search extends from our own solar system, with Mars and the icy moons of Jupiter and Saturn, like Europa and Enceladus, being prime candidates, to exoplanets orbiting distant stars. The recent advancements in telescopic technology and space exploration missions have significantly enhanced our ability to search for these criteria beyond Earth. Missions such as NASA's Mars rovers, the James Webb Space Telescope, and the Transiting Exoplanet Survey satellite are designed, in part, to gather data relevant to these criteria. By studying the atmospheres of exoplanets, analyzing soil and ice samples from other planets and moons, and detecting the faint signals that might indicate the presence of life, scientists are expanding our understanding of where and how life might exist in the cosmos. The discovery and study of exoplanets, planets orbiting stars beyond our solar system, have dramatically expanded the search for life in the universe. Before the 1990s, Exoplanets were merely theoretical. However, the confirmation of planets orbiting other stars has shifted them into the realm of reality, profoundly impacting our understanding of the universe's potential to harbor life. Exoplanets have expanded the search for life by revealing the sheer diversity of planetary systems and the wide range of environments in which planets exist. With thousands of exoplanets discovered to date, astronomers have identified a broad spectrum of types, from gas giants many times the size of Jupiter to rocky planets that might resemble Earth. This diversity challenges our preconceptions about where life might exist, pushing the boundaries beyond the traditional habitable zone to include a variety of planetary environments. The discovery of exoplanets in the habitable zone, the region around a star where conditions may be right for liquid water to exist on a planet's surface, has been particularly significant. These worlds, sometimes called Goldilocks planets, are of keen interest because liquid water is thought to be essential for life as we know it. Observations of such planets, including their size, orbit, and the characteristics of their stars, help scientists assess their potential habitability. Technological advancements in telescope and observation methods have been crucial in exoplanet discovery and study. Techniques such as the transit method, which detects planets as they pass in front of their stars, and the radial velocity method, which observes the gravitational pull of planets on their stars, have been instrumental. These methods not only allow the detection of exoplanets, but also provide information about their atmospheres, compositions, and, in some cases, surface temperatures. The study of exoplanet atmospheres has opened new avenues in the search for biosignatures, the chemical indicators of life. By analyzing the light from stars as it passes through a planet's atmosphere during a transit, scientists can identify the presence of molecules such as water vapor, oxygen, methane, and carbon dioxide. These molecules, especially when found together in certain ratios, could suggest the presence of biological processes. Future missions and telescopes, such as the James Webb Space Telescope, are expected to enhance our ability to detect and analyze exoplanets further, providing more detailed insights into their atmospheres and, potentially, surface conditions. These advancements hold the promise of identifying more planets in the habitable zone and possibly detecting direct evidence of life. The possibility of time travel has long fascinated scientists and the general public alike, sparking debates and studies within the realms of theoretical physics and cosmology. According to current scientific understanding, certain interpretations of the laws of physics suggest that time travel could, in theory, be possible, though the practicalities and implications are far from being understood or realized. The theory of relativity, proposed by Albert Einstein, provides the foundational framework that allows for the possibility of time travel under specific conditions. Relativity divides into two parts: general relativity, which describes the force of gravity as the curvature of spacetime caused by mass and energy, and special relativity, which addresses the physics of moving bodies at high speeds and how they experience time. General relativity introduces the concept of time dilation, a phenomenon where time passes at different rates depending on the strength of the gravitational field or the speed of movement through space. For instance, clocks on satellites in orbit around Earth tick slightly faster than those on the surface due to the weaker gravitational pull. This effect, although minuscule, has been confirmed by experiments and has practical applications such as adjustments made to account for time dilation in the GPS satellite's atomic clocks. More dramatically, general relativity predicts the existence of phenomena like black holes, regions of space-time where gravity is so strong that not even light can escape. The theory suggests that near a black hole, time would slow down significantly compared to farther away, hinting at the possibility of different paths through time. However, the extreme conditions near a black hole would likely be unsurvivable, and thus, while theoretically interesting, they do not offer a practical method for time travel. Another theoretical possibility for time travel comes from the concept of wormholes, bridges in space-time that could connect distant points in space and time. If wormholes exist and could be stabilized, a big if requiring exotic matter with properties not yet observed, They might allow for travel between different times as well as locations. However, the existence of wormholes remains speculative, with no empirical evidence to date. Quantum mechanics also introduces scenarios that challenge our classical understanding of time. Certain interpretations suggest the possibility of effects preceding causes under specific conditions, though translating these quantum effects to the macroscopic world of human experience remains a significant challenge. Despite these theoretical possibilities, the practical realization of time travel faces monumental challenges. Issues such as the violation of causality, the principle that causes precede their effects, and the enormous energies required for such feats make time travel into the realms of science fiction rather than practical science at our current level of understanding and technology. How do black holes theoretically enable time travel? Theoretical physicists have proposed that the unique structure of space-time around a rotating black hole could be used to travel through time. As an object approaches the ergosphere, it could theoretically take advantage of the black hole's rotation to enter a closed, time-like curve, a path through space-time that loops back on itself. This would theoretically allow for travel into the past or future, depending on the trajectory taken by the object. Another related concept is the wormhole, or Einstein-Rosen bridge, which is a theoretical tunnel connecting two separate points in space-time. If such a tunnel could exist and be stable, and one end of the wormhole were close to a black hole or another massive object, time dilation could cause time to pass at different rates at either end of the wormhole. Traveling through the wormhole could then, in theory, allow for movement through time as well as space. However, these theoretical possibilities come with significant caveats and challenges. For one, the extreme gravitational forces near a black hole, especially near the singularity, would likely destroy any known form of matter, making survival impossible with current technology. Moreover, the existence of stable wormholes and their practical use for time travel remains purely speculative, requiring exotic forms of matter with negative energy densities that have not been observed. Additionally, these concepts challenge our understanding of causality, the principle that causes precede effects. Time travel to the past, in particular, introduces the possibility of paradoxes, such as the well-known grandfather paradox, where a time traveler could potentially prevent their own existence. Quantum mechanics, the branch of physics that deals with the behavior of particles at the atomic and subatomic levels, fundamentally challenges our classical understanding of the universe. It introduces concepts that are profoundly counterintuitive and have far-reaching implications for our conception of reality. Unlike classical physics, which describes a world of certainty and predictability, quantum mechanics unveils a realm where probabilities and uncertainties dominate. One of the cornerstone ideas of quantum mechanics is wave-particle duality, which reveals that particles such as electrons exhibit both wave-like and particle-like properties. This duality defies the classical notion that entities in the universe must be either waves or particles, suggesting instead a more complex underlying reality. Alongside this, the Heisenberg uncertainty principle states that certain pairs of physical properties, like position and momentum, cannot both be precisely measured at the same time. The more accurately one property is known, the less accurately the other can be determined, challenging the deterministic view of the universe that underpinned classical physics for centuries. Quantum entanglement, another startling discovery of quantum mechanics, shows that particles can become linked in such a way that the state of one, no matter how far away, instantly influences the state of another. This phenomenon, which Einstein called spooky action at a distance, questions the very foundations of classical ideas about causality and locality. Moreover, the principle of superposition allows particles to exist in multiple states simultaneously until they are observed. This idea, often illustrated by the thought experiment known as Schrödinger's cat, in which a cat is considered to be simultaneously alive and dead until observed, challenges our everyday experience of reality, where objects exist in definite states. The role of observation in quantum mechanics suggests that the act of measurement plays a crucial part in determining the state of a system. a notion that has puzzled scientists and philosophers alike, leading to questions about the nature of reality and whether it exists independently of observers. Quantum tunneling further stretches our understanding by allowing particles to pass through barriers that would be insurmountable according to classical physics. This not only demonstrates the non-intuitive nature of quantum mechanics, but also underscores its practical significance, influencing the development of technologies such as transistors and nuclear fusion in stars. Through these concepts, quantum mechanics challenges our classical views of the universe, introducing a world where probabilities replace certainties, and where the very act of observation can determine the state of reality. It paints a picture of a universe far more strange and interconnected than previously imagined, forcing us to reconsider not only the nature of particles and forces, but also the fundamental nature of reality itself. To expand on quantum entanglement, entanglement was initially considered so bizarre that Einstein referred to it as spooky action at a distance, expressing skepticism about its implications for the principles of locality and realism in physics. However, numerous experiments have since confirmed entanglement's reality, demonstrating its potential to fundamentally alter our understanding of information transfer and connectivity in the universe. The potential of entanglement to connect distant parts of the universe lies not in sending information faster than light, which would violate the theory of relativity, but in creating correlations that can be realized instantaneously. This has profound implications for quantum communication and computing, suggesting the possibility of inherently secure communication channels or computing systems that operate at unprecedented speeds due to their entangled components. Beyond its applications in technology, entanglement raises intriguing questions about the fabric of the universe itself. Some theories suggest that entanglement could be a fundamental feature of space-time, possibly related to the quantum nature of gravity. This has led to speculative but fascinating ideas about the universe's interconnectedness, with some physicists pondering whether the Big Bang could have entangled particles across the cosmos, weaving a hidden tapestry of connections that underpin the universe's structure. While entanglement does not allow for the transfer of information in a way that would enable faster-than-light communication or travel, it does challenge our understanding of separation and independence at a fundamental level. The instant correlation between entangled particles, regardless of distance, suggests a level of unity in the quantum realm that transcends classical spatial separation, hinting at a deeper, perhaps still undiscovered principle governing the cosmos. Quantum computing, with its roots deeply embedded in the principles of quantum mechanics, represents a seismic shift in computational power and capability, potentially revolutionizing our exploration of the cosmos. Unlike classical computers, which use bits as the smallest unit of information, quantum computers use qubits. These qubits can exist not only in states corresponding to the binary 0 or 1, but also in states where they are both 0 and 1 simultaneously, thanks to quantum superposition. Furthermore, qubits can be entangled, meaning the state of one qubit can depend on the state of another, no matter the distance between them, enhancing the quantum computer's ability to process and analyze information exponentially faster than its classical counterpart for certain tasks. This leap in computational power could transform our exploration of the universe in several ways. First and foremost, it would enable the processing of vast data sets generated by telescopes and space probes far more efficiently than is currently possible. The cosmos is a treasure trove of data, from the cosmic microwave background radiation detailing the early universe's conditions, to the light from distant stars and galaxies that can tell us about the universe's expansion rate and the distribution of dark matter. Quantum computers could analyze this data much more swiftly and deeply, uncovering patterns and correlations that might remain elusive to classical computing methods. Quantum computing could also revolutionize the field of simulation. Astrophysicists rely on simulations to understand complex, dynamic processes such as galaxy formation, black hole behavior, and dark matter distribution. These simulations are immensely computation-intensive, especially when trying to model phenomena over cosmic timescales or the interactions of billions of particles. Quantum computers, with their superior processing capabilities, could simulate these processes with a level of detail and speed unattainable with classical computers, providing new insights into the fundamental workings of the universe. Another promising application is in the optimization of telescope arrays and the planning of space missions. Quantum algorithms are well suited to solving optimization problems, which could enhance the design and arrangement of telescopes to maximize their observational capabilities or optimize the trajectories of space probes to explore the solar system and beyond more efficiently. The search for extraterrestrial life could benefit from quantum computing through the analysis of atmospheric data of exoplanets for signs of life, known as biosignatures. The precise and complex calculations required to distinguish these signatures from myriad cosmic phenomena could be more feasibly performed with quantum computers, accelerating the search for life beyond Earth. Quantum computing holds the potential to decode the mysteries of the universe by significantly enhancing our ability to process information, simulate complex systems, and analyze the signals we receive from the farthest reaches of space. As this technology advances, it may not only redefine our exploration of the cosmos, but also deepen our understanding of the fundamental laws that govern it, bringing us closer to answering some of the most profound questions about the universe and our place within it. Cosmic voids, vast expanses of empty space that punctuate the cosmos, are as intriguing as the galaxies and stars that have captivated humans for centuries. These voids are not merely absences of matter, they are critical components in understanding the large-scale structure of the universe. Spanning millions of light-years across, voids are the largest structures in the universe, defined not by the presence of something, but by the lack of it. They contain few galaxies compared to the universe's denser regions, making them appear as enormous bubbles in the cosmic web, a complex network of filaments that connect galaxies and galaxy clusters with voids in between. The existence of cosmic voids and their properties provide valuable insights into several aspects of cosmology, including the universe's expansion, the nature of dark matter and dark energy, and the initial conditions of the cosmos following the Big Bang. Voids are sensitive to the dynamics of the universe's expansion because their evolution is influenced by the gravitational pull of matter in the surrounding filaments and sheets. As the universe expands, voids grow larger, acting like stretch marks in the fabric of space-time. By studying how voids expand and evolve, astronomers can infer the rate of the universe's expansion and the influence of dark energy, the mysterious force accelerating this expansion. Furthermore, the shape and distribution of cosmic voids can tell us about the nature of dark matter, the unseen substance that exerts gravitational force and helps shape the large-scale structure of the universe. Voids form in regions of space where the density of dark matter is lower than average, and by analyzing the size and distribution of voids, scientists can test models of cosmic structure formation and the properties of dark matter. The patterns of voids, along with galaxies and galaxy clusters, are also a cosmic echo of the early universe's conditions. Tiny fluctuations in the density of matter in the early cosmos, as seen in the cosmic microwave background radiation, grew over billions of years into the structures we observe today. The size and distribution of cosmic voids are thus a direct link to these initial conditions, offering clues to the processes that shaped the universe shortly after the Big Bang. Cosmic voids also serve as natural laboratories for studying the physics of the universe under extreme conditions of low density. In these vast empty spaces, the influence of dark energy and the laws of gravity can be observed without the complicating effects of dense matter. This makes voids ideal for testing theories of gravity and the behavior of galaxies and intergalactic gas in environments very different from our own Milky Way. The Great Attractor is a gravitational anomaly located in the vicinity of the Hydra Centaurus supercluster, about 250 million light-years from the Milky Way. This mysterious region of space exhibits a gravitational pull that affects not only our galaxy, but also thousands of other galaxies in its vicinity, drawing them towards it at velocities of hundreds of kilometers per second. The existence of the Great Attractor was inferred from the peculiar velocities of galaxies, movements that cannot be accounted for by the expansion of the universe alone. Galaxies, including the Milky Way, are moving towards the Great Attractor in a flow known as the Laniakea supercluster, which encompasses the Great Attractor. The nature of the Great Attractor has puzzled astronomers since its discovery in the 1970s. It lies in a region of space that is heavily obscured by the Milky Way's galactic plane, making direct observation challenging with optical telescopes. This area, known as the Zone of Avoidance, is filled with dust and stars that block the light from objects beyond our galaxy, hiding the Great Attractor from view and complicating efforts to understand its true nature. Despite these challenges, observations using X-ray, infrared, and radio wavelengths, which can penetrate the dust, have revealed a dense concentration of galaxies and galaxy clusters in the region of the Great Attractor. These studies suggest that the Great Attractor is not a single massive object, but rather a large concentration of mass anchored by a complex of galaxy clusters, intermingled with dark matter. Dark matter, which does not emit or absorb light, contributes to the gravitational force exerted by the Great Attractor. The influence of the Great Attractor on galaxies is primarily gravitational. It affects their motion, pulling them towards its center in a phenomenon known as gravitational attraction. This movement is part of larger cosmic flows that govern the motion of galaxies across the universe, shaped by the distribution of matter and energy on the largest scales. The gravitational pull of the Great Attractor is so significant that it impacts the velocities of galaxies over hundreds of millions of light-years, indicating the presence of a very massive structure. Rogue planets, celestial bodies wandering through space unattached to any star system, present a fascinating puzzle in the cosmic landscape. These planets exist outside of solar systems, drifting alone in the vastness of space, and their discovery has challenged our traditional understanding of planetary formation and the dynamic history of the universe. The existence of rogue planets is primarily attributed to the chaotic nature of young star systems. During the early stages of a star system's formation, planets and planetesimals can be ejected from their nascent systems due to gravitational interactions with other bodies, such as larger planets, or as a result of the dynamic rearrangement of the system's architecture. Another scenario involves close encounters with passing stars or galaxies, which can gravitationally unmoor planets from their orbits, sending them into interstellar space as rogue planets. Rogue planets can range from rocky worlds not much larger than Earth to gas giants many times our planet's size. Without a host star to illuminate them, rogue planets are incredibly difficult to detect. They are often discovered through gravitational microlensing events, where the gravity of a rogue planet acts as a lens, magnifying the light of a distant star as the planet passes in front of it from our perspective. The study of rogue planets offers a unique window into the universe's history and the processes that shape planetary systems. For instance, the number and mass distribution of rogue planets can provide clues about the frequency and violence of gravitational interactions in young solar systems, offering insights into the commonality of planet ejection events. Rogue planets challenge our understanding of planetary environments and the potential for life. A rogue planet that retains a thick atmosphere could trap enough heat from its formation to sustain subsurface oceans, raising intriguing possibilities about the habitability of these dark, wandering worlds. The discovery of rogue planets also expands our conception of where planets can exist, suggesting that planetary bodies are not confined to the traditional zones around stars. Investigating rogue planets can also contribute to our understanding of the distribution of matter in the galaxy, including dark matter. As these planets drift through the galaxy, their interactions with the gravitational field can offer indirect evidence of the dark matter's distribution and properties. The ultimate fate of the universe is a question that has puzzled astronomers and cosmologists for centuries. With the advancement of observational techniques and theoretical physics, several leading theories have emerged, each proposing a different scenario for the end of the universe. These theories are grounded in our current understanding of cosmology, particularly the nature of cosmic expansion and the properties of dark energy and dark matter. One prominent theory is the heat death or the Big Freeze, which suggests that the universe will continue expanding indefinitely. Over trillions of years, stars will exhaust their nuclear fuel and die, galaxies will disperse, and black holes will evaporate through Hawking radiation. The universe would become a cold, dark, and lifeless expanse, with temperatures gradually approaching absolute zero as the energy becomes evenly distributed across an ever-expanding space. This scenario is considered the most likely outcome based on our current understanding of dark energy, which appears to be causing the acceleration of the universe's expansion. Another theory is the Big Crunch, the antithesis of the Big Bang, where the universe's expansion eventually halts and reverses, leading to a catastrophic collapse. In this scenario, galaxies, stars, and ultimately the entire universe would collapse into a singular point, possibly leading to another Big Bang. However, the discovery of the accelerating expansion of the universe has made this scenario less likely, as there seems to be insufficient mass and gravitational pull to reverse the expansion. The Big Rip is a more dramatic variant that depends on the nature of dark energy. If dark energy increases in strength over time, it could tear apart galaxies, stars, planets, and eventually the fabric of space-time itself. In this scenario, the expansion of the universe accelerates to the point where all matter is ripped apart at the atomic level, leading to a universe devoid of any structure. A less discussed but equally fascinating theory is the Big Bounce. This concept suggests that the universe undergoes an infinite series of expansions and contractions. Rather than ending, the universe bounces back from a big crunch, leading to a new Big Bang and a new universe. This cyclical model, while speculative, is appealing for its symmetry and the possibility that our universe is just the latest iteration in an eternal cycle of cosmic rebirth. Lastly, there's the possibility of a quantum death, where quantum effects at the smallest scales could lead to the decay of the vacuum state of the universe. This would result in a bubble of lower energy vacuum expanding at the speed of light, altering the laws of physics within it and rendering the universe as we know it unrecognizable. This scenario is highly speculative and depends on unknown aspects of quantum gravity and particle physics. Dark energy, a mysterious force that is driving the accelerating expansion of the universe, plays a pivotal role in cosmological models predicting the universe's ultimate fate. Since its discovery in the late 1990s through observations of distant supernovae, dark energy has been a central focus in understanding the dynamics of the cosmos. It constitutes about 68% of the total energy content of the universe, yet its nature remains one of the greatest mysteries in physics. The influence of dark energy on the universe's fate hinges on its properties, particularly whether its strength changes over time. If dark energy remains constant, as suggested by the cosmological constant model proposed by Albert Einstein, the universe will continue to expand at an accelerating rate. In this scenario, galaxies will move further apart, stars will burn out, and the universe will cool as it heads towards a state known as the Big Freeze or heat death. In this cold, dark, and empty universe, all matter would be so far apart that interactions between particles become effectively non-existent. Alternatively, if dark energy grows stronger over time, a scenario known as the Big Rip could occur. In this dramatic end, the force exerted by dark energy would eventually overcome all other forces, including gravity and the electromagnetic force holding atoms together. Galaxies, stars, planets, and eventually even atoms would be torn apart by the relentless expansion of space, leading to a universe in which no structures, not even the smallest particles, could exist. Conversely, if dark energy were to decrease in strength or reverse its effects, the universe's expansion could slow down, halt, and potentially reverse in a process leading to the Big Crunch. This scenario imagines a universe contracting back into a hot, dense state, possibly setting the stage for another Big Bang and a new universe. However, current observations supporting the accelerating expansion of the universe make this outcome less likely under the prevailing understanding of dark energy. There's also the possibility that the nature of dark energy could lead to other, less understood scenarios. For instance, if dark energy's properties are not constant, but change in ways that we have yet to comprehend, the universe's fate could be something entirely unforeseen, challenging our current cosmological models. The role of dark energy in determining the universe's fate underscores not only the dynamic nature of the cosmos, but also the profound impact of seemingly intangible forces on cosmic evolution. As researchers strive to unlock the secrets of dark energy through observations of the cosmic microwave background, distant supernovae, and galaxy clusters, we edge closer to understanding not just the universe's ultimate fate, but also the fundamental nature of reality itself. The influence of human activities extends far beyond our planet, reaching into the solar system and beyond, in ways both direct and indirect. While the vastness of the cosmos means that our actions have a negligible impact on the universe at large, certain human activities do leave a cosmic footprint, illustrating the broader implications of our presence in space. Space exploration, for example, directly interacts with the cosmic environment. Human-made objects have been sent to all the major planets in our solar system, from the Voyager probes that have crossed into interstellar space to rovers exploring Mars. These missions carry with them the potential for contaminating other worlds with Earth-based organisms, despite rigorous sterilization protocols. Theoretically, if microbial life were to take hold on another planet or moon, it could influence the astrobiological landscape, altering our understanding of life in the universe. On a more immediate scale, human activities have created a belt of artificial satellites and debris orbiting Earth. This space junk not only poses a risk to operational satellites and space missions, but also contributes to a layer of technological detritus around our planet. As we continue to launch satellites and other missions, this cloud of artificial material becomes a characteristic of Earth, potentially observable from distant worlds. If other civilizations exist and have the capability to observe our solar system, this layer might serve as an indicator of technological activity on Earth. Light pollution is another aspect of human activity with cosmic implications. The artificial light that illuminates our nights spills into space, altering the natural nighttime environment of Earth as seen from space. This pollution makes it more difficult to observe the cosmos from Earth-based telescopes, potentially hindering our ability to study the universe. Moreover, the change in Earth's nighttime appearance could, in theory, be detectable by distant civilizations, signaling the presence of technologically advanced life. The theoretical concept of the Kardashev scale, which classifies civilizations by their energy consumption and manipulation of their environment, suggests that advanced civilizations could have a significant impact on their planetary systems or even their galaxies. While humanity is not currently at a level where our energy use significantly alters the solar system, this scale implies that the progression of civilizations could eventually lead to cosmic-scale effects. Human activities also contribute to the study and understanding of the cosmos. Theoretical research, observations, and simulations conducted by humans have expanded our knowledge of the universe, from the behavior of particles to the structure of galaxies. In a way, our intellectual endeavors leave an imprint on the cosmos by unraveling its mysteries and disseminating this understanding, influencing future generations and potentially other civilizations that might come into contact with our knowledge. On the topic of exploring our place within the cosmos, we encounter the simulation hypothesis. This hypothesis suggests that our reality, including the Earth and the universe, might actually be an artificial simulation. Popularized in the 21st century by philosophers and technologists like Nick Bostrom, this hypothesis posits that if a civilization were to reach a high enough level of technological advancement, it could create computer simulations that are indistinguishable from reality for the consciousnesses inhabiting them. Essentially, beings within such a simulation would be unaware of their true nature. They would consider their experiences, interactions, and the world around them as genuinely real. The hypothesis draws on several lines of reasoning, including the advancement of video game technology as a familiar example. Modern games feature increasingly complex and realistic environments that are a far cry from the pixelated landscapes of earlier generations. Following this trajectory, proponents argue, it's conceivable that future technology could simulate entire universes with such precision that the simulated beings within them would possess consciousness and self-awareness, believing themselves to be real. A core argument supporting the simulation hypothesis is the idea of ancestor simulations. If it's possible to simulate consciousness, future civilizations might run simulations of their ancestors to study their history, behavior, and decision-making processes. If such simulations are numerous, the argument goes, it's statistically more probable that we are living in one of the countless simulations rather than in base reality. Critics of the simulation hypothesis raise several objections, from the feasibility of simulating an entire universe in such exquisite detail to the ethical implications of creating conscious beings capable of experiencing suffering. Moreover, some argue that the hypothesis is unfalsifiable. That is, there's no empirical test that could definitively prove or disprove our existence in a simulation, placing it outside the realm of scientific inquiry. Another area of debate centers on the nature of consciousness and whether it can indeed be simulated. This question touches on deep philosophical and scientific mysteries regarding what consciousness is and how it arises. If consciousness requires a substrate that cannot be digitally replicated, then the simulation hypothesis might not hold. In our quest for knowledge, we've learned that the universe expands uniformly in all directions, with no discernible center in a physical sense, challenging our innate desire to find a central point of reference, a prime mover. Perhaps then, the center of the universe is not a location to be charted, but a concept to be explored, residing in the heart of our quest for understanding. It might be said that the center is everywhere and nowhere, mirrored in the depth of human curiosity and our ceaseless endeavor to comprehend the cosmos and our place within it. This journey of discovery, fueled by wonder and the collective human intellect, positions us all at the center of a universe, bound by the limits of our perceptions and the breadth of our imaginations. Do you believe there is a center? If not now, has there ever been a center of the universe? Let us know your thoughts in the comments below. Thanks for watching.